Hello and welcome to Beam call number 5 already. Today's topic is APS, attester-proposer separation, and we're going to have Julian run the call today. But before that, I'm just going to give a very, very quick presentation to set a little bit of context. Okay, so already call number 5. In 2 weeks, we have call number 6. We're going to have two sets of presentations. One of them by Vitalik, who actually implemented 3SF in a matter of a few days in Python. So he'll be presenting his stuff. And we're also going to have Roberto, Francesco, and Luca also talk about the work that they've been doing. And again, on June 29th, we have Beam Day Can, and there should be a QR code, maybe not. Okay, QR code is in the slides from last time. So today we have Julian who will be presenting. Now, one kind of master link, if you're not already aware of it, is aps.directory. I believe this is a Notion doc that is maintained by Julian, and it has all sorts of other links to continue your exploration of APS. Now, what are we trying to achieve with APS? So in my opinion, one of the big value propositions of APS is this notion of Zen staking, where we really want the stakers, the attesters, the operators of these validators to be as unsophisticated as possible. And today, without APS, there's a few things that the operators have to worry about. One of the first things that they have to worry about is MEV. So they have to install an extra piece of middleware called MEV-Boost. They have to pick some relays, and there's all sorts of complications there as to which relays you pick, depending on whether you're regulated or not regulated, and blah, blah, blah. There's also this issue of MEV spikes. Basically, you get selected as a proposer at random. It's a sort of a lottery. And when you do get selected, there's kind of the second order randomness where sometimes you happen to get really lucky because it's, for example, a period of high volatility when there's a lot of MEV. And these spikes are actually unfriendly to decentralization because the median validator, your typical validator, will make less than your average validator. And the reason is that every once in a while, someone wins a very, very big jackpot, and that will skew the distribution. It will move the average up, but your median typical validator will not get access to that jackpot. And so that incentivizes the creation of smoothing pools, which adds extra centralization and complexity. Another issue related to MEV-Boost is this notion of timing games. If you are a maximally rational operator, you're going to want to play timing games, and that adds to the sophistication of being a validator. And then a final thing related to MEV is that sometimes you receive a bunch of MEV, but it's kind of MEV that maybe you didn't want to receive. So for example, it could be the proceeds of a hack, or it could be the proceeds of sandwiching, or something like that. And here there's a bit of a moral dilemma, like should you return the funds or not? And that's something that I believe the validator should not be exposed to. And then there's a kind of a whole second class of things that the validators potentially have to worry about in the not so distant future, which is related to this notion of proposer commitments. So there's a piece of software called Commit Boost that allows proposers to opt in to commitments, one of which is pre-confirmations. But if you have pre-confirmations, you probably also have the equivalent of relays, which is the gateways. And also you have, if you want to play the pre-confirmation game, you need to add collateral. And so all of these things basically add complexity that to the validators that we want to remove. And basically the idea here is called attester-proposer separation, where all of the sophistication falls on the proposer, which is a separate entity, one which is assumed to be sophisticated and can play all of those games. And the attesters can just be super dumb entities that run on Raspberry Pis or on smartwatches. Now, if we zoom out to all of the consensus layer improvements, this is a slide that I had in my DEF CON talk. In my opinion, the least de-risked is actually attester-proposer separation. And the reason is that there isn't really a clear answer as to what we should do. I think what we've done so far is that we've explored the design space, but we don't know, and we have multiple possible candidates, but we don't know which candidate to pick. And the reason is that there are some fundamental trade-offs that have to be made. But if we look at trying to give a score in terms of de-risking, I'd give issuance and randomness a 5 out of 5. And the reason is that these would not be part of the beam chain. Smarter issuance would either be done pre-beam or post-beam, and VDF randomness would be done after the beam fork. These numbers are subjective, but in my opinion, we're making fantastic progress in de-risking fossil, which may come in Amsterdam. We already have an EIP for it. I think 3SF is also very much de-risked. And Poseidon 2 and in general, snarkification of the whole chain, I think, is very, very much de-risked. And if you're interested in keeping track with all of the progress on ZKVMs, we have a separate call called the Eve Proofs call, which you're welcome to join. And one of the reasons why I'm relatively happy with Poseidon 2 is because even if there's some sort of a small attack on Poseidon 2, there is an easy way to defend against it, which is just to add more internal rounds to the hash function to boost the security. And then there's a few things here which I'd give a 3 out of 5 in terms of de-risking, which are things that we're still investigating. They're somewhat new. They've never been done before. So quantum signatures have never been done before. Rainbow staking and smaller slots have never been done in the context of Ethereum. But overall, I'm not too worried. And this brings us to the final point, which is attester-proposer separation. I think this is the one topic that has the lowest score from a de-risking perspective. And the fact that we're talking about it today hopefully is a forcing function to make progress here. So again, today's speaker is Julian, researcher at the Ethereum Foundation, and I'll share the floor with him. Julian, you may take it from here.
Awesome. Let me share my screen. Can you see my screen?
Yep.
Perfect. Okay. Well, first of all, thanks for the great context setting for APS. Yeah, so I would say APS to me feels like we're firewalling attesters and proposers very much. And as Justin said, there doesn't seem to be one silver bullet solution. So what today I'll be presenting is some background information of why we want it and how we've thought about achieving it. Then go into a specific proposal that maybe threads the needle quite well between all of the different things that we want from APS. And lastly, explain if we don't go for this silver bullet-ish solution that relies on some heavy assumptions, how can we relieve some of these assumptions, and what does that mean for what we get out of the mechanism? So the goal is really to help people understand the design space, see what we have done so far, and show what decisions basically have to be made. And finally, how we can make those decisions. Okay, so I'll try to go through the background very fast because probably a lot of people here are familiar. And yeah, I don't want to lose people throughout. However, also feel free to ask questions during the presentation, as it's nice to just keep up with the presentation, and probably other people will be wondering about the same things. So I'm going to start with a quick recap of how we select proposers today. Suppose there is the blockchain, and Alice has built block 99, Bob has built block 100, and then we need to select who builds block 101. Today, Ethereum does so by randomly selecting a validator from the validator set, who then becomes the proposer of the block. And I put this asterisk on the die because actually we don't randomly select a validator within block 101 to become the validator of block 101, but we do so up to 2 epochs in advance because of the limitations of the randomness that we have in Ethereum today. Then this randomly selected validator mostly chooses a builder via MEV-boost, as most of you will be familiar. And so this builder pays the validator something for the right to construct the block, and the validator gives the builder its execution proposing rights. And APS is fundamentally about changing the way that we select proposers here. So instead of doing this indirect method where Ethereum randomly picks a validator via random, and this random validator then probably sells its execution proposing rights to the builder, APS aims to achieve that the Ethereum protocol itself can choose the builder directly. So that's what the direct link here signifies. And so why would we actually want APS? Well, Justin actually introduced APS in the end of 2023 as a method to combat proposer timing games. And timing games refers to the economic benefits a proposer can get by proposing a block after the owner's proposer deadline. And therefore, that proposer can include maybe more transactions, or it can better extract MEV. And so intuitively, it's just you're extending the slot duration, and so you're getting some more MEV out of that. And it's bad for the network because of this effect of geographic centralization. So if you are a proposer who's close to other proposers, you can extend your block very late because your block will reach the other proposers very quickly. So let's say that you're in the US and there are lots of other US-based proposers around you. They'll receive your block very quickly and they'll vote for your block and it will probably still become canonical. Let's say now that you're a proposer on Antarctica or something, then there will be very few proposers around you. So you have to account for the time that it takes for your data to be transmitted over the network and reach the other testers, and that they'll actually vote for you. So timing games have this geographic centralization incentive, which was at least the main motivation to get rid of it and go for attester-proposer separation. Justin initially proposed execution tickets, which works roughly as follows. The Ethereum protocol sets up an execution ticket market, and this market can look like a variety of things, but the main idea that it looks like is people buy their tickets, where tickets have a fixed price and the supply is flexible. And they do so quite far in advance. So for example, 32 slots in advance. And this removes any of the timing games incentives because 32 slots in advance, it's unlikely that there's any new information coming in this extra tiny bit of time that you have to play timing games. So the execution proposers, who are similar to the builders today, they buy their tickets in this market far in advance, and their proceeds of this market are burned. And then when it comes closer to the time of proposing, one of these execution proposers is randomly picked, and the probability of winning is proportional to the amount of money they spent on tickets. So assume that there are 2 execution proposers who want to win the market. And one has bought 10 tickets and the other has bought 20. Then the person that bought 20 tickets has a 2/3 probability of winning, and the person that bought 10 has a 1/3 probability of winning. But they both pay for those tickets, and they won't get any refund if they don't become the actual winner of the market. And separately, the Ethereum protocol appoints a beacon proposer, and the beacon proposer is in charge of making a beacon block, which we won't go too much into, but for context, it means it's a block that contains attestations and consensus information that's important to progress the chain. Then another proposal for APS has been execution auctions, which is proposed by Barnaby. And it's maybe a simpler design that looks more like MEV-boost today. The Ethereum protocol would use one of the beacon proposers, so the beacon proposer of slot n, to sell the execution proposing rights of slot n plus 32. And we use this 32 slot difference again to prevent any timing games. And this, up until now, it looks very similar to MEV-boost, but the difference is that the Ethereum protocol forces the beacon proposer to pick the highest bid. And that's signified here by this little burn emoji, which represents MEV-burn. And so MEV-burn is a tool that allows Ethereum to force someone to pick the highest bid, and then the auction proceeds are burned. So is that, if that's clear for everyone, I'll continue, but if there are questions, feel free to ask.
Yeah, feel free to raise your hand at any time.
Perfect. I'll just continue, but if there are questions, feel free to ask throughout the presentation. Okay. So execution tickets and execution auctions have been proposed quite a while ago now. Execution tickets at the end of 2023 and execution auctions at the beginning of 2024. And so why it has taken us some time to further APS is because of two main critiques. One of them is centralization, and the other one is multi-slot MEV, which I guess is related to centralization. First, I'll go a bit into the centralization arguments. So there are two separate arguments. First, by Quintus and Connor from Flashballs and Nethermind, respectively, who made this post, when to sell your block. And what it says is that it compares today's MEV boost, where builders build their block and they include transactions that pay priority fees, they include searcher bundles that pay them some MEV, and so they know how much their block is worth. And so when they bid in the market, they know, well, at least if I bid less than what my block is worth, I'll be making some money. And so bidding is quite risk-free in that sense. However, now if you do this auction 32 slots in advance, or the sale of the execution rights 32 slots in advance, then you don't have this, I guess, base return that the builder would get. And so the builder has to predict what it thinks the block might be worth, and this is centralizing because it has more risk. And auction theoretically, it also means that the auction is probably more common value, which leads to something called the winner's curse. And then separately, there's a centralization argument made by Jonah, David, and Fahad, and Malesha Max separately, which I like to call no information means no specialization. So remember that in execution tickets and execution auctions, the sale is done quite far in advance, so 32 slots in advance, which would be about like 6 minutes. And compare that to today, where it's done maybe a second in advance, or maybe even less. And so today you could be in a situation where a builder would win the slot because they're very, very good in an environment when there's a lot of volatility. Another builder may win when there's a lot of exclusive order flow, and yet another builder may win when there is some NFT spike or something. And that is to say that builders sometimes have a specialization, and that is when they win. But then if you do the auction far in advance, the specialization is not so clear because these builders don't have information about whether the volatility will be very high in that specific block, or what the market's environment will exactly look like. And so people aren't bidding based on a block conditional on some market events like volatility, but they're bidding on a block unconditional. And what that means is that there's likely to be one proposer or just a few who have by far the highest unconditional expected value of a block in the future. And so there's no specialization, and that means that this unconditional expectation rules who wins the market, which then would lead to more centralization. And I want to note that these papers, they mostly apply to execution auctions done far in advance. Execution tickets have slightly different characteristics, and there's been some great work from Mike Nuder, Planoff Media, and Tim Lufgarden, who found that execution tickets are fundamentally more decentralizing than execution auctions. And intuitively, this is the case because the winner in execution tickets is randomly chosen. And so sometimes the winner is not the builder with the highest valuation. So going back to the example of having one builder that buys 10 tickets and the other one that buys 20, probably the builder that bought 20 tickets thinks the block is worth more. But still, there's 1/3 probability that the other builder, the one that bought 10 tickets, wins. And so this is somewhat more decentralizing. And then the next argument is multi-slot MEV. And so I'll first just quickly recap what multi-slot MEV is it refers to the fact that a builder is more likely to extract more value if it can optimize its MEV extraction strategy over multiple blocks than over just one block. So imagine Alice, who controls 3 blocks in a row. What it could do is it runs its MEV extraction strategy in block 99, it does so in block 100, and it does so in block 101. However, it doesn't actually optimize over all of the 3 blocks simultaneously. Then these individual optimizations are likely to be worth less than if you optimize over the entire set of 3 blocks. It's quite intuitive why this would hold. If you see it as an optimization problem, optimizing over 3 blocks all at once or optimizing over 3 individually is kind of similar to optimizing with fewer constraints or with more constraints. And clearly, if you optimize with more constraints, your optimal solution isn't going to get better. So your optimal amount of MEV extracted isn't going to get more. However, that doesn't necessarily mean as well that it is actually going to get more. It could also be equal. I think here we need to look a lot more at whether there is more evidence of actually more MEV being extracted if there are multiple slots optimized over jointly. Intuitively, it would be logical if that were the case because there's just a wider search space. And so it could be that you can attach transactions to each other in more combinations, allowing you to extract more MEV. Yeah, Justin.
Yeah, it's probably worth highlighting that if you'd like to help with this problem of understanding how big multi-slot MEV is, that's a meaningful problem to work on. I think we're going to get a little bit more insight with ETH-gas. I think ETH-gas is trying to harness multi-slot MEV, and we'll see from the market that bidding action, whether or not it is more valuable. And I think we're also starting to work with some of the builders to try and get some insights. But if you're an independent researcher interested in multi-slot MEV, do get in touch.
Yeah, thanks a lot for that call out. We'll talk more about multi-slot MEV. So I'll make a few hints of where specifically more insights will be very valuable. But I think this is one of the biggest blockers for APS currently. Yeah, so thanks for the shout out. And so that brings us basically full circle on the background, and we would go further on the digital data. And so you may have noticed now that we started APS with trying to prevent timing games, but now we get at a list of digital data that's far bigger. So actually, we want to get a lot more out of APS. So one of the things that we want to get is a more competitive builder market. And this could be achievable via the execution tickets arguments made by Mike that I just mentioned. If that's execution tickets means that you randomly select a winner. And so sometimes a winner is chosen that may not have the highest valuation for a block, which is more decentralized in the market. And also, we don't want to make an APS instantiation that just leads to lots of multi-slot MEV extraction. So ideally, we would be even like theoretically resistant against multi-slot MEV extraction. However, another path is also to look at whether there actually exists this multi-slot MEV and how large it is. Yeah. And then these last two digital data are the no MEV for validators, which basically applies to the timing games argument and pre-conf friendliness. And so I haven't talked much about this last one, but basically what it means is that we want the next execution proposer to always be known. And so pre-confirmations can be issued by an execution proposer if it knows that it controls a future slot. If you don't know that you can control future slots, people are unlikely to buy pre-confirmations from you, and you can't really sell them. And so to ensure that the pre-confirmation market can flourish, we want that the next execution proposer is always somewhat known. And so the no MEV for validators applies to the timing games. We don't want MEV for validators because that would be an incentive for timing games. And also the reward variance argument that Justin made in his introduction, where sometimes a validator can win 1 ETH, 1,000 ETH, or 0.0001 ETH. And this is an incentive for joining a staking pool. And so we want to remove all MEV from validators, not just the timing MEV. And here I also want to quickly pause and say that this is basically where APS and ePBS connects. So ePBS is Enshrined Proposer Builder Separation, which is a slightly older proposal than APS. And ePBS aims to just remove the relay rule. And so APS also removes the relay rule, but it does so while also trying to achieve these other digital data. And so in PBS, the relays facilitate the fair exchange between a validator and a builder, where the validator gets some payment for its block building rights and the builder gets the block building rights. In APS, this relay isn't really necessary because the fair exchange is spread out over more time. So a builder pays in slot n and it receives its good in slot n plus 32. And so the protocol kind of acts as a relay, but in a simple way. Okay, and so here's my proposal, which I'd like to propose maybe not as the solution that fixes APS, but as more of as a thought experiment of what the frontier is of the trade-off space that we can establish. And particularly, I want you to keep in mind that we need to make a trade-off basically between multi-slot MEV and pre-confirmation. And so here's how the proposal would work. instead of doing execution tickets 32 slots in advance, we would just do it 2 slots ahead. And this would help a bit with the unconditional expectation argument that would lead to more centralization. And so we use execution tickets, and we don't do it that far in ahead, so that the block builder market can stay somewhat decentralized. Bids flow into block 98. Let's say that we're selling the execution proposing rights of block 100. Then bids flow into block 98 as regular transactions, and they are recorded in a smart contract. So let's say that Alice buys 10 tickets, Bob's buys 15, and Charlie buys 5. Then that's recorded in a contract as follows. And then after block 98, the market is closed and this contract won't be altered anymore. So for the execution proposing rights of 100, you can only bid in block 98. So you can't do so in block 99. Then block 99 is proposed, and after block 99 has been committed to, so after the execution proposer signs over it and sends it to the network, some randomness is revealed, which then picks the winner from the smart contract of the execution ticket markets. And again, it does so proportional to how much the builders have paid. And then this randomly selected winner becomes the execution proposer of block 100. And so this has a few characteristics that I'll go to in a second. So first I'll dive more into the bidding process. So as I mentioned, that bids would be considered regular transactions. And we want to do so because then they can be propagated on the execution layer, which will likely enjoy more censorship resistance than the consensus layer at the time of the beam fork. So one reason that this is the case is because of fossil. So consider transactions that are included in block 98. Potentially, the current builder of block 98 is also a bidder in the market. And maybe this builder doesn't want to have any competition within the execution ticket market. Then it would be incentivized to censor some of the transactions from its competitors. But something that we can do about that is fossil. And so since these transactions aren't time sensitive because they are designed to evade timing games, they can be submitted on time, included via fossil, which is an inclusionist scheme that's also proposed for the beam chain, and included in the block. Yeah, Justin?
I just want to relay 4 questions that have been asked in the chat. If you do want to ask the question, feel free to unmute. But the first question is, does this assume SSF or not?
It does not assume SSF necessarily.
Right. Yeah, from my perspective.
Can I therefore ask then a question then, if it doesn't?
Yeah.
So let's suppose that we don't have SSF and we sell a slot and you have the right to propose a block, whatever time in advance. So you bought this right and now you equivocate. And you're a builder, you're not a validator. How do we deal with safety? I mean, we have an accountable safety that has to deal with this double voting, double proposing. How do we deal with equivocations if we don't have SSF, if we haven't committed to a particular for choice?
Yeah. Yeah, so that's definitely a good question. I'd say, first of all, the equivocations that we have today for block proposals aren't like consensus critical in the same sense that FFG equivocations are. So we slap equivocations on, we slap slashing on block equivocations basically to incentivize people to not mess with consensus in this way, but it's not the same as FFG equivocations. So we could deal with equivocations of execution proposers in a variety of ways. We could go the fossil route of basically, if you do equivocate, then all of your execution blocks are not considered, or we could do some slashing. I'd like to say APS, at least, I mean, there definitely has to be more work into this, but APS has less of like an impact on for choice than perhaps EPBS has, specifically because maybe we don't have to satisfy honest builder safety and unconditional payments for the validator because this fair exchange doesn't happen in real time, let's say. So if you go back to this slide, you can see that the bids flow into block 98 and the good is delivered in block 100. Whereas in EPBS, you have a more difficult setting because the bids flow in block 98 and the good has to be delivered in block 98. And so not having to satisfy this fair exchange within the same block potentially makes it easier, but it's definitely something that we'd have to look into more.
Another thing to note is that we don't really have SSF. We have 3SF, which has a latency of 3 slots. And so in this case here, if the finality gadget takes 3 slots and we have a 2-slot execution target mechanism, it's not going to help. So yeah, in my mind, SSF and APS are largely orthogonal. Another question from Will: does this assume delayed execution?
It doesn't necessarily assume delayed execution.
Terrence asked, do you need better randomness than RANDAL?
Yeah, so I'll get into that. But this, so at the beginning, I mentioned here that this proposal relies on like a heavy assumption. And so perhaps it's not the proposal that should be implemented, but it's meant to show basically the trade-off space. And so I'll get into that into the coming slides. But yeah, so the randomness here assumes a good randomness, which is better than the current random that we have.
Alpha asks, what if the bid itself is front run?
So the bids are like very, very simple objects, basically. So it's the number of tickets that you want to buy, where the tickets have a fixed price and the winner ID. And that means that so if your ticket is the winner, which ID will propagate the execution block. And so you're basically buying tickets at a fixed price. So there's not really, I guess, yeah, your orders are order agnostic. It doesn't matter for you whether you're front runner or not.
Terrence?
But wouldn't you have some sort of like timing game? Because like, say if your ticket is in the mempool, right? And then I see what other people are bidding, and then I will bid right after. So wouldn't the Nash equilibrium be in a way that everyone just bids towards the deadline, like right at the deadline type of thing? So have you considered like encrypting the bids or something like that?
Yeah, so encrypting the bids, I think, would be very nice. That's another reason why doing it on execution layer would be nice, since encrypted mempools are, I guess, have more applications on the execution layer as well. Whether the Nash equilibrium would be very late or very early, I think it's not so easy to tell. You could also imagine people bidding very early. Yeah, and in a sense, these tickets are very order agnostic. And so, yes, you have some. It's nice for you to know more about how many other orders there are in the block. But it doesn't depend on that so much. And also, there's no new information, like by assumption, I guess there's no new information revealed during the slots that would make your order like more well-placed at the end than at the beginning. Okay, now I'll try to go through it a little bit, and if there are still questions, I'll take them in a bit, or maybe at the end, and I'd love to discuss more. But I think, yeah, just explaining it a little bit more now will make some more stuff clear. And so getting back to the bidding process, these bids are the number of tickets that you want and the winner ID. And so the winner ID is the ID that will distribute or propagate the execution block if this ticket did indeed win. And so that's nice with encrypted mempools, because that means that the sender doesn't necessarily have to be the person who would also be the winner of the auction. And so the sender address might not even be encrypted in encrypted mempools, and so the winner ID would be encrypted. And so then getting to a bit more of the specifics of the market, I would propose a fixed price flexible supply market. And there's been some work, notably by Christoph Stradel from Flashbots, who showed that this is a better market for decentralization and competition compared to having a flexible price fixed supply. And we can make the price very low. So for example, 1 Gwei. And then bids are committed to 2 slots ahead instead of the 32 slots ahead, which would be better for some market competition arguments, as I've laid out before. Doing this on execution layer, where we don't care as much about the timing games that happen. So remember, APS is a response against beacon proposer timing games. And so the timing games played by those that are also attesters. We don't want attesters to play timing games because we have an honest majority assumption on the attesters, but we don't have an honest majority assumption on the execution proposers. And so APS doesn't actually get rid of timing games as a phenomenon. It just means that there are no beacon proposer timing games anymore. There could still be execution proposer timing games, but since all of this lives on the execution layer, the bidding process lives on the execution layer, this doesn't hurt the honest majority assumption that we have on the testers. And then finally, we use the censorship resistance that's on the execution layer, and in that sense we get MEV-burn for free, which is a sentence that's more often thrown around with APS. And here the for free part means that we don't have to implement another availability committee that you would have to do with MEV-burn. And actually Fossil and MEV-burn look very similar, as in they say it is a committee of people who say we have seen certain bids at certain amount of time, and they must be included in the block. And so, yeah, they look very similar, and in that sense, we don't have to do the work of implementing another MEV-burn mechanism. Yeah, Justin?
So Enrico asks a relevant question. Can these bids fill up the Fossil capacity? If so, will this reduce the user transaction censorship resistance capacity?
Yeah, so I wouldn't say they would fill up the Fossil capacity. So Fossil doesn't actually increase the supply of gas that a block has. And blocks today have a supply of 36 billion units of gas. And then there's the 1559 mechanism that aims at creating enough demand to satisfy basically the target. So the base fee fluctuates such that on average, there should be about the target limit, the target amount of gas demand. And so Fossil doesn't affect the amount of supply or demand there is necessarily. And so these tickets, they could just be included in Fossil, and Fossil has about 128 kilobytes of room available within across the 16 inclusion lists. And if I understand correctly, blocks are around 100 megabytes today. And so there should be more than enough supply in Fossil to be able to get all of the transactions into the block. That being said, I guess these transactions, they do consume gas, and so they do consume some network resources. Doing it on a consensus layer, however, also consumes network resources. So if you do it on a consensus layer, these bids also have to be processed. And so potentially there are some differences here, but I think from first principles, they should be using roughly the same amount of network resources. Okay. Yeah, Justin, was there anything else?
So Data always asks the question, does this mean we're only burning the MEV from public mempool transactions? And I think it was answered in the chat, whereby Fossil is only used as a censorship resistance gadget. It's not used as an MEV oracle. You can still use whatever external information you want to price the bids.
Yeah, exactly. So yeah, Fossil is not the MEV-burn part. It's just the inclusion, which is similar to MEV-burn, I guess. The amount of MEV that is burnt is just the number of tickets times the price at which the tickets are sold, which is irrespective of Fossil. And then getting to the winner selection part, we do this thing where the smart contract contains the bids or the orders for the amount of tickets, and then after block 99 is revealed, some randomness is revealed that is applied to the smart contract to pick the winner. This is a relatively complicated setup, so I'd like to explain why this setup might be nice if it is feasible. And so first of all, we have a minimal look ahead. And so the block proposer of block 99 doesn't know who would be the winner of the block of the execution block in slot 100. And so this means that while building 99, you can't optimize over slot 99 and slot 100. So you can't extract multi-slot MEV in that sense. And so that's quite a hard guarantee of it's just not going to happen regardless of whether there is a lot of multi-slot MEV available or not. And then finally, why we don't pick, for example, the winner in the beacon block of slot 100 is that we want to enable pre-confirmations as well as possible. And so for pre-confirmations, we want that the next execution proposer is almost always known. And this is the case here. And the only time when the next execution proposer is not known is with this delta t, which is the time between the release of the execution block 99 and that the randomness is revealed. And so getting this delta to be as small as possible would mean it's better for pre-confirmations. Then finally, I guess the elephant in the room has been this randomness. And so this randomness is a big assumption. One way that we could get it is using a threshold committee, where a threshold committee reveals randomness after the execution block has been revealed. But this imposes a liveness assumption, which would be a a large decision to make, and even though it might be possible and it might have some other nice use cases, it is a big assumption to be aware of. Another way that we could go is using encrypted mempools and using the post-state root as our randomness. So let's say that a transaction is included in an encrypted way into a block and then decrypted afterwards, and I guess executed or maybe the decrypted version of that transaction or the decrypted version of a set of transactions is used as randomness. Then the builder of the execution block of slot 99 doesn't know the contents of the decrypted version of what they had included in encrypted way. And so usually encrypted mempools also rely on some sort of threshold committee, but there are other options like sealed transactions from Anders, which is an ETH research post, which you could read. But this is also no free lunch. So there are some considerations with MEV issues potentially. So yeah, I just want to emphasize that this randomness is a very big assumption and not something to be considered lightly. Why I still propose this is to show basically the fundamental trade-off that there exists between multi-slot MEV prevention and pre-conf friendliness. So in the following, I'll propose two other APS implementations, which go for either preventing multi-slot MEV completely or ensuring that it's very friendly to pre-confirmations. And these two don't rely on randomness. So the randomness is only necessary if you want to both prevent multi-slot MEV and have pre-confirmations. If you want either of the two, you don't need it. Are there any questions on that? If not, so I'll move on. Okay, so then I'd like to present execution tickets, which is basically the same as the execution tickets proposal that we've seen before. And I'd like to say that this is basically the way to go if you want to optimize APS for pre-confirmations. And so the mechanics are fairly similar to the previous proposal. Bids flow into a block. They can be execution layer transactions stored in the smart contracts. It could also be done via the consensus layer. It doesn't matter too much, but then if you do it on the consensus layer, you need to ensure that you have some more censorship resistance, which is doable in this setting. Then some blocks later, randomness is revealed. And in this case, we could still use the RANDAO that we have today. And that means that with some sort of randomness, which is biasable, the winner is chosen of who will be the execution proposer of block 100. And this winner will be known for some time between the block that the randomness is revealed and the block that the proposer has to propose. And so because the proposer is known during that time, it can sell pre-confirmations to users. You could do so, for example, 10 minutes in advance, so that proposers, so the execution proposers can sell subscriptions or other fancy types of pre-confirmation use cases. But yeah, the trade-off here is that because you have this look ahead, you have multi-slot MEV. And so that goes to show that the look ahead is like fundamentally necessary to have pre-confirmations, but it's also fundamentally the problem for preventing multi-slot MEV. And then you could also go the other way of saying we don't care as much about pre-confirmations and we just want to ensure that there's no multi-slot MEV. And I think the best way to do this is to host an auction in the beacon block of 100. So note that this mechanics are quite different from the previous proposals, as in here, it's an auction and it must be done in the beacon block of 100. So in this case, bids flow in and MEV-burn is used to observe all of the bids that exist and say all of these bids must be included in the beacon block. And again, the proceeds, I guess, are burned. With this, we can't do execution tickets anymore because we don't have this randomness that was just revealed. So we would do an auction and just an auction in which the highest bidder wins and those that lose, they don't pay their bid. And so you can sell the execution proposing rights for block 100 in the beacon block of 100. But the problem here is that it's slightly unfriendly to pre-confirmations. And that is because in the time difference between the execution block of slot 99 and the beacon block of slot 100, there's a time where the next execution proposer isn't known. And so that's signified with the delta T here. And it means that in this time period, the users can't receive pre-confirmations, which would mean that the average time to inclusion would be higher, which is bad user experience. It is like really, really good against multi-slot MEV because bids come in after the last execution block has been committed to. And so you can't optimize over multiple blocks because even if you were to leave open like a multi-slot MEV opportunity in block 99, then you would basically have to bid for this for what you left open again in block 100. And so you can show that multi-slot MEV is unincentivized to extract multi-slot MEV. A downside here is that we do need an additional availability to committee to ensure that MEV burn is possible because the bids are on the consensus layer. And so here again, I want to show how this relates to the earlier proposal with the very good randomness that I assumed. So the JIT execution auctions was basically the proposal that I was working with before. But if you want to decrease this pre-conf unfriendliness to the minimum possible, then what you could do is choose after, like the best you can do is choose just after the execution block of slot 99 has been revealed to decrease this delta T. And to do that, you need to do this randomness basically. And so the randomness shows basically like you can't do better than that. So you need to make a decision there. And so in summary, Justin had proposed in chatting with Justin, there came up 3 tracks. One is the randomness track. So looking whether this randomness is indeed possible. Doesn't it impose too much liveness assumptions on Ethereum? Like, do we actually want this? And maybe is it useful for other applications? In that case, it would be interesting to explore further the first proposal. If we find that this randomness is just impossible or it's not a trade-off that we're willing to make, then we have to choose either pre-confirmations or preventing multi-slot MEV completely. And to inform this decision, that's really the crux of what we have to do in the coming time. And so Justin mentioned that multi-slot MEV is really an area where people can contribute, and I want to reiterate that call. So some interesting work would be like to see, is multi-slot MEV really a big deal or not? And that's also something that we can learn over time. And similarly, whether pre-confirmations will gain adoption. And so that's to say, we basically need to make a trade-off here. And then finally, do we still want APS? Because it's become a bit of a lower volume topic, I say. I think that's partly because we've seen that timing games at the moment aren't that big of a deal. This is a photo from Tony's timing.pix, and it shows over there, what is it, the last 14 days, the amount of ETH profit cumulatively that proposers have gained over time. The green dashed line is those that do play timing games, and the red dashed line is those that don't play timing games. And you can see that the green line has been above the red line for most of the time period, but then they converge, and there's quite a little difference there. So perhaps timing games are not that big of a deal currently, but they may be in the future, of course. That being said, APS is still interesting because it does remove relays, which ePBS also does. And it does implement MEV burn, which is independently desirable as well. However, potentially we need to use either no multi-slot MEV or pre-conf friendliness. And so that decision is something that we need to work on. Yeah, so that's all for what I had. So thanks a lot for your attention. And as Justin mentioned, there's this website, aps.directory, which contains, as far as I'm aware, an exhaustive list of all of the APS work. And you can find me on Signal or Telegram here if you'd like to be contributing to this work.
Amazing. Thank you so much, Julian. On the topic of having to make a trade-off and potentially waiting more time for us to gather more information and make a more informed decision, a potential strategy here is actually to have multiple APS subspecs, version A and version B, and then just pick one or the other closer to the beam fork. And the good news is that APS is not super complicated. I mean, maybe there is a bunch of complexity hidden in the randomness gadget, but if we assume no fancy randomness, there's these 2 flavors that we could go with, and we could even potentially have a 3rd flavor, assuming the fancy randomness. So I'll just repeat the question that was answered in the chat, just for the listener. Do ticket prices go up and down depending on demand?
Yeah, so I'd say in principle that's a design decision. There's been some work now showing that it's nicer to just have a fixed price. And so I think for now we should go with just setting a fixed price that's very low. So there's always at least one person willing to buy one ticket. And then letting the supply be flexible. And it can be shown then that that's better for market competition, basically.
I guess one thing here to note is that there's two variants of execution tickets. There's one which, if you've been selected as a ticket winner, your ticket is removed from the pool of tickets. And then there's one where it's not removed. And I guess you could call the second version execution staking, which is basically you have a number of units of GUI, and then your probability of winning the auction is proportional. But when you win, you don't lose any of your stake. And here, the way that you pay is through opportunity cost. I guess yet another flavor of execution staking would be, in addition to paying with opportunity cost, there would be some sort of negative issuance curve. And so, for example, if we want to have at most 1 million ETH staking to become execution proposers, we could have a curve that goes to negative infinity around 1 million cap. Thomas asks, but then you should be able to buy multiple tickets in one transaction, right? Arbitrarily many tickets in one transaction.
Yeah, an order can just specify how many tickets they want.
Ladislaus asks, would you mind repeating why in the JIT execution auction scenario, the competitive execution proposer market assumption would still be satisfied?
Yeah, that's a great question. So I'd say the competitive market assumption is something that's it's hard to make very explicit and precise, I guess, and it's all on the spectrum. So what we know about the competitiveness is that execution tickets is better than execution auctions, and doing it closer to the deadline. So doing it just in time is better than doing it far in advance. And so what you're trading off here is you can do execution tickets, but then you have to do it further in advance, basically. So execution tickets is better, further in advance is worse. Or you can do execution auctions, which I guess is worse, and just in time, which is better. So the trade-off is there, but it's hard to quantify what exactly the outcome is.
Thomas asks, at least to me, it sounds like we're trending more towards a pre-cons will be important rather than multi-slot MEV is a huge deal.
Yeah, I'd say so probably. There to some extent both like an induced demand type of arguments. Like pre-confirmations, we don't know yet how large they will be at what time frame, but there's definitely lots of potential. And then multi-slot MEV, I mean, we don't know how much is possible today, but there might be some early signs that it's not so much. But I'm saying that very carefully, and it's something that we need to consider more.
I mean, one consideration is whether or not access to flow is the predominant thing that determines centralization as opposed to multi-slot MEV. And so it's possible that it's not a huge deal and it's relative to other things.
That makes sense, but I'd say multi-slot MEV is not a centralization argument necessarily. It's also just mostly like a bad user experience argument. And so there is like the centralization part, which may be dominated by other factors, but separately it still has some negative externalities.
Right. So two more things we'd like to know about multi-slot MEV is one, will it materialize in the current market? Because in the current market, we do have a look ahead of, let's say, 32 slots. And so in theory, we could have multi-slot MEV. And And then the second thing that would be nice to know, I forgot what I wanted to say. In any case, I'll come back. Mark asks, how close are we to having the fancy randomness we need with VDFs?
Yeah, so I'd say here we probably can't rely on VDS. So I said like threshold committee or doing this sealed transactions thing with encrypted mempools that doesn't rely on a threshold committee. VDFs here are a bit tricky because you have to get the timing very, very good. That being said, I'm no expert on VDF, so perhaps Justin can say more there.
Yeah, so if you want low latency randomness, VDFs is the exact wrong tool that you want. Yeah, the only way that I know to get low latency randomness is using threshold cryptography, and that has all sorts of complications. One of them is that you need a fallback for liveness. Another one is that it's unclear how to do threshold cryptography in a post-quantum way. Most of the solutions I know use elliptic curves. And then there's also an attributability problem, which is that if there is collusion and the threshold assumption is not held, then you actually can't detect that there is collusion. So yeah, it is definitely a powerful tool potentially, but it's also one that comes with trade-offs. And I did remember the thing that I forgot, which is it would be nice also to see how the applications find ways to defend against MEV. So for example, we might see batch auctions, or we might see custom sequencers, and that might inform also the multi-slot MEV discussion. Lotus.
Yeah, I wanted to comment that to study the centralizing force of having the auction predicting for the future, we can actually get hard data now in how it's going to work with the fast lane in Arbitrum, for example, where you have bidders for the next minute. It's not exactly the same as APS, but the market dynamics might be similar, where people with information are betting on how the market's going to move in the next minute or so.
Yeah, that's a very interesting point. Thanks. We should study.
And another market that might yield insights is Solana. And the reason is that Solana has 4 slots in a row per proposer. And so, yeah, we might see, a very sophisticated market say, I'm willing to reserve the first 2 at a different price than kind of reserving each individually, something like that. Okay, we're exactly at the hour, and there are no more questions in the chat. I'll just give a few more seconds for questions to come in. Otherwise, thank you so much, Julian, for the great discussion. And yeah, in a couple of weeks, we're going to have 3SF as a topic. Thank you so much, everyone, and have a great day. Bye.
Thank you. Bye.
Thank you. Bye.
Bye-bye.